Today I'm visiting Semidynamics here in Barcelona on a very hot and warmy day, and I'm meeting up with Roger Espasa. Roger Espasa, I do pronounce it right. It's the English version, I think, of Roger Espasa.
Yes,
okay,
good.
Here at Semidynamics, and Semidynamics is working with the RISC-V technology. And now, before I explain everything, I first like to ask Roger, can you give a bit of a background about Semidynamics? What is the company?
Absolutely. We started back in 2017. We started more of design services. We did RISC-V work for an American company called Esperanto Technologies for a couple of years.
Yeah.
They produced their chip. We're very proud of the work we did for them. And after that, we decided to create our own RISC-V IP that we could put on the market. And that's what we've been doing more or less since mid-19. Took a couple long years to get the IP ready, and now we're go-to-market phase. Make our products known to the world, explain our advantages and why we're doing it.
Okay, good. Now RISC-V, due to the nature of RISC-V, is a reduced instruction set architecture. Right. Not many instructions basically you can work with, but I believe that you with your company is focusing on enhancing the performance and capability of this RISC-V architecture. What is your approach? How do you see possibilities to enhance the performance of RISC-V architecture?
Right. There's two long answers to your question. I want to warn you. The one is that RISC-V is great because being reduced, but at the same time being extensible, allows you to really optimize around what's there. So just by being simple, it enables more creativity around the microarchitecture that supports the RISC-V ISA. That's one. Second one, it's extensible. And among the extensions that are already approved by the RISC-V International Foundation is one that's very important, which is the vector extension. And the vector extension provides a ton of performance. And so there's a document that anyone can read, and you read that document and you can implement a vector unit based on that vector specification. And that's what we've done. And we've made a very special vector unit looking to the people that want a lot of performance.
Okay, and this vector extension, that has been part of your development, part of your activities?
Indeed.
Yeah.
So I was part of the working group that defined the extension, so we've been involved from day one. But then once it's ratified and it's approved and the world says, okay, this is what all of us in the RISC-V ecosystem are going to do, then each vendor competes in how well you implement that specification. And we've been working on that and actually put a lot of work with out-of-order vector unit and a technology we call Gazillion that go very well together.
Yeah. So basically you've done that. Finito, you're done. What is next?
In this business, you're never done, right? The same way the big guys, Intel and these guys, you have to have a new product with a certain cadence. The base is done indeed, and it's ready to go to customers, but we never stop improving, analyzing the performance, looking at the software that our customers want to run, and then analyzing why is that particular software maybe not running as well as we expected, and then making tweaks and changes to improve. So yes, it's finished, but no, it's never finished. We will forever be pushing the performance.
We're working at that. Yeah. So if you can give a sort of a profile of what sort of applications you're looking at with RISC-V, because I see RISC-V going in all directions. It goes from controllers for hard disk to IoT solutions to. But can you give a sort of a profile? What sort of customers do you have in mind working with these vector extensions and cores, etc.?
There's a couple of ways to say it. We have both a solution for the people called the control plane. So if you take just our cores without the vector unit, which we've just discussed, that's very good for control plane. But then there's a lot of people are coming to us from the edge world, AI world, saying, wow, I used to have a camera or a device that control a robot or who knows what. And it used to be allow me to call it a dumb device that connected, but now everyone wants to run AI on the edge, right? So those people now want a control plane and a data plane. So for the control plane, everyone's moving to RISC-V. For the data plane, people are saying, wow, the vector extension is really interesting because I could have now my, whatever it is, my edge chip, then do a little bit of AI on the edge and improve my product. And that's the kind of customers coming to us is people that have lots of data computation needs. Oddly, at the same time, low power needs, so that makes it difficult and challenging, or they're moving a lot of data. So you did mention SSD controllers. Hey, those things are moving a lot of data, and a lot of people on an SSD want to do more, right? So anything that's moving a lot of data, image pipelines, SSD pipelines, or just AI inference and training, these are the kind of customers we're getting.
Okay. And now I also understand that this factor extension, also the cores, etc., is a sort of a flexible approach you're having. So what is flexible? What do you mean by that?
Again, maybe the analogy is engines, right?
Okay.
It's an engine, and you can have 2 cylinders, 4, 8. Well,
okay.
We have from 4 cylinders to 32, right?
Okay.
It's if your audience will forgive my analogy, I hope.
But
effectively.
It's understandable for me. That's also important.
think. I'll name a competitor. This is not okay, but NVIDIA talks about CUDA cores, right? And you have a GPU with 200 CUDA cores, 2,000 and 3,000. That's the element of compute, right? The vector unit, same thing. A vector unit contains vector cores inside, and the customer says, Roger, I'm okay with just 8 vector cores, or wow, I need more. I need 16, or I need 32. That's a choice that our customer makes, right? We take that vector unit and connect it directly to a RISC-V core. That's different from a GPU. In a GPU, we're all used to having the CPU, and then a long PCI Express, and then the GPU, which is great. The GPU is fantastic, but it's far away, difficult to program. By having the GPU, you break it into pieces in groups of 16, and you connect them to RISC-V cores. Suddenly, it's easy to program. There's no latency. And actually, you have the same performance because you took the other thing, you broke it into pieces and connected to cores. So that's our approach.
Yeah. Now, you're working client-specific, I assume. You're not making one chip for all, but you just talk to your clients. And so, if I'm a client and I come to you, say, I need this special IE on the edge device. I need to recognize whatever it is, red balls from green balls or whatever. How long is that process? So I need to have it, in a half year's time or in a year's time. What is the normal lead time from when you first start talking with your client to the actual, product, the actual tape out of the processor?
We usually do like 3 phases, and the first phase is sitting with the customer, the client, and saying, what do you really need? And that's actually usually longer than we all expect, because as we ask questions, then they solidify what they want, and so this takes a little bit of a while. Then there's a hopefully a short legal phase where we agree on pesky details like money, right? And right after that, we start doing the changes that they want.
Sure.
We get the changes to them pretty fast in the form of a bit stream for an FPGA. Obviously, that's not the final product, but we want to get it back to them so they can test their software and try it out. And because in this loop, they will say, oh, wow, we thought we wanted this, but sorry, can we change? And then while they're testing the software, we start verification, which is the longest part of the process. So we try to overlap these things, get them back very fast, working, let's call it prototype, because that thing cannot be tape out. And then while they're testing it and running with it and their software people are learning, we are doing verification. So then we meet at the tape out agreed date, so everything is ready for them to tape out on their schedule.
Okay, so but these are long stretches of time.
We get to them something working in usually less than 3 months, but actually
less than 3 months.
Yes, but verification may take more than 6. So the
total,
right? So that's where we try to overlap their evaluation with the verification. Right? It's a way for them, for us to help them tape out sooner. Right?
So Semidynamics, we're here now in Barcelona. In 4 or 5 years' time, what do you feel? What is your outlook, and what do you feel is possible for a company?
We're very, very ambitious. So I should refrain from telling the truth. No, we really are getting out to the market, presenting our IP. We have a close eye on the chiplet market. We think chiplets are going to change the way chips are done. So we're monitoring that very closely. We want to be part of that. We're making some actions in that direction to make sure that we're ready for when the chiplet world explodes, which will explode. And after chiplet, it's a little bit too far to know, but we're not short of ambition.
Okay.